In this video, I'm going to talk about how focal length is defined for a lens, sort of how we determine when we're making a lens, what the focal length will be, and then in a future video, we'll connect the focal length to the actual sort of focusing that a lens does, focusing or diverging, and how the focal length relates to the image that you're going to get from that lens. So first off, we're talking about lenses. There are two different types of lenses that we could be interested in. Converging lenses, where the sides of the lens bulge out, or a diverging lens, where the sides of the lens bulge inward here. And as you would probably guess from the name, a converging lens, if light rays come in from the left, they will get focused towards a point on the right. Those rays are going to come together from a converging lens. They're going to converge. Whereas for a diverging lens, if light rays are coming in from the left, when they leave the right side of the lens, they will be traveling apart, diverging away from each other. You'll also sometimes hear a converging lens referred to as a convex lens, and a diverging lens referred to as a concave lens. These are just other names that are used for these types of lenses. You'll also, if you look at the picture here, you'll notice that this picture that I grabbed off the internet labels this as a biconvex lens. That just means that both the left and right sides of this lens are curved, rather than one of the sides being flat. I'll use the general term convex lens, regardless of whether both sides are curved or just one. Both of these lenses have a focal length, and the focal length is defined in the same way for each lens. But for this learning module, I want to focus on convex lenses. I want to focus on converging lenses. We'll save diverging lenses for the next learning module. So let me pull the concave lens out of there. And the focal length, we have a mathematical expression for it. 1 over f equals n minus 1 times the quantity 1 over r1 minus 1 over r2. So let's step through this equation one term at a time. The f here is the focal length. So this convex lens has some focal length that we denote by f. N here is the index of refraction of the lens. So depending on what material, glass, Pyrex, various types of plastic that we make the lens out of, that will determine the N there. That 1 is the index of refraction of air. So we're assuming that what's outside the lens is air. That's why we put the 1 there. If it weren't air, if it were a lens sitting in water or something like that, then instead of this being 1, it would be the index of refraction of water. And so we would have N lens minus N water. But usually the lens is just exposed to air, and so we write it as N minus 1. Moving along, R1 is the radius of curvature of the incoming side of the lens. So here in this picture, light is coming in from the left. So this is the incoming side of the lens. This side has some radius of curvature that we denote as R1. And we'll say more about what exactly radius of curvature means in just a moment. And then R2 is the radius of curvature of the outgoing side. So this right side in this lens is also curved, and it may be curved the same amount as the left side, or it may be curved a different amount. And so that radius of curvature for the right side of this lens is denoted by R2. So the radius of curvature basically means if we took this lens, this curved side, here talking about the incoming side on the left, if we took this curved side and imagined it as part of an entire circle, that circle would have some radius. And this radius of this circle, this imaginary circle that the front side of the lens is part of, is the radius of curvature of that lens. Of that side of the lens, so what we're calling R1. Similarly, we could match the back side of the lens to another circle of some size, and the radius of that circle we call R2. And so this radius of curvature is a measure of how curved the lens is. You can sort of picture in your mind, if this lens were less curved, then it would kind of come out around here, and we would need a bigger circle. So a big radius of curvature means that the lens is flat. A small radius of curvature means that the lens is more tightly curved. So the more curved that the lens is, the sort of smaller of a circle it's part of, and the smaller its radius of curvature. Now, you might be concerned, going back to these past two pictures. In these pictures, it looks like R1 and R2 are about the same. In that case, would our equation be 0 if we have 1 over R1 minus 1 over R2? If those distances, R1 and R2, are the same, it looks like this expression might be 0, which might be troubling. And it turns out that's not the case because of some sign conventions that we have embedded in this equation. And so, for this lens, I want to define two different sides and talk about the sign conventions that we use. So we have light coming in from the left, coming into the lens from the left and going out of the lens to the right. The side that the light comes in from, we call the virtual side, and the distances on this side are going to be negative distances. There's one exception that we'll talk about later, but in general, any distance that I measure to the left of the lens to the side that light's coming in from is going to be a negative distance. Any distance that I measure to the right of the lens is going to be a positive distance. And this right side of the lens we refer to as the real side. And these names we'll talk more about later, but they basically mean if light comes in from the left, we would expect the image to show up on the right side of the lens. And so where we expect the image to show up is what we call the real side, and where we define positive distances. So for a convex lens, R1, that was the radius of curvature of this incoming side, that was measured over here, so R1 is a positive number. The radius of curvature of this outgoing side, that distance was measured over on the left side, on the virtual side, and so R2 is less than 0. So even if R1 and R2 are the same distance, one of those numbers is positive, one of those numbers is negative, and so you don't get 0 in our equation. So coming back to our focal length equation, F is the focal length, N, the index of material of the lens, depends on what we make the lens out of. 1, that depends on what's outside the lens. We assume when we write 1 that there's air outside the lens, but if we stuck the lens underwater, the focal length of that lens would change. And then R1 and R2 both depend on how curved the two sides of the lens are. And the smaller those radii, the more curved the lens is. So this is, if we were building a lens, how we would determine the focal length of that lens. So my contacts are made out of a certain material with a certain index of refraction, and both sides of my contact lens have a certain curvature to them, which determine R1 and R2, and together how curved my lens is and what it's made out of determines the focal length for my lens. In the next video we'll connect this to actually thinking about where do these rays converge. How does the focal length relate to focusing or diverging the light?